Last time we were taking a look at section 1.2 and we were talking about patterns. And we had gotten to the point where we had created general forms for sequences that we were given, and we talked about that being inductive reasoning. Okay, so I want to go through just to remind you again how we create those general forms, because that's usually the part where students struggle when they get to this particular homework assignment, is to create how we create these formulas. Okay, so let me remind you how we did that. So for an arithmetic formula, we noticed that we added the same number every time. When we add something multiple times, that's the same as multiplication. So what we do is we take that value, which is called the common difference, and we multiply that by the letter or the variable n. Okay? N represents the number of term we're on. The way we decide what we add or subtract in the end of the problem is by looking back at the original first term. If I plug in the number 1 here, I get 3. Now, if 3 had been my first term, then I'd be done. I wouldn't have to do anything else. But it's not my first term. My first term is actually the number 1. So what I do then is I add or subtract whatever I need in order to get the value I currently have, which was 3, to become a 1. And so there's a minus 2 there. And then you can verify that you did it right by checking other terms. So if you plug in the number 2, it should be the second term in the sequence. So if you plug in 2 into 3 times 2 minus 2, we get 4. We're in good shape. That's what we should be getting. If I didn't, then I've probably got an error in this minus 2. Okay? And we can continue down the sequence like that to make sure that we actually have the right value. Geometric. Geometric, we notice that we multiply by the same thing every time. Repeated multiplication is exponents. So this common ratio, this number I multiply by, is the base of an exponent, which exponent is always going to be n minus 1. And the reason it's n minus 1 is because when I plug in the number 1, I get 0, and this whole thing becomes 1. Anything to the 0 power is 1. Okay, so this resets, by having the exponent n minus 1, it resets everything that's in parentheses when n equals 1 to the value 1. And then what goes in front is simply the first term of my sequence, 3. And again, you can check to make sure it works by plugging in different values. So just for fun, we'll plug in n equal to 3, which should be my third term, or 12. So I plug in 3. 3 minus 1 is 2. 2 squared is 4. And then 4 times 3 is 12, which is my third term. So I can check to make sure I have the right terms. So that's the part where people usually come into problems, so I wanted to go through it a second time. All right, we're going to change. One other thing is the very end we talked about is this inductive or deductive reasoning. And we decided that it was inductive because we started with a general pattern and we tried to decide specifically an equation or a formula or something to predict what's happening in the future. We tried to make a prediction based on a general pattern, okay, that we thought we saw. All right, example number 2. Example number 2 says that we're going to use the nth term formula given to find the first 5 terms of the sequence. And then the second thing we're going to do is to identify if the sequence is arithmetic, geometric, or neither. So let's start with like letter I, if you will, on this. How am I going to find the first 5 terms? What do I do? Yeah. We're going to plug in all the numbers from 1 to 5, one at a time. So if we're finding the first one, we take 5 times 1 plus 6, and what do we get? 11. And then the second one, we do 5 times 2 plus 6, and what do we get? 16. Now, you don't necessarily have to show the plugging out stuff that I've done. You could just do that in your head. I'm okay with that. I'm just writing it down in case someone didn't see what I was doing to get the numbers, or maybe didn't at the very first or whatever. So if you plug in the 3, what do you get? And you might start to notice a pattern even to know what the next 2 are. I went from 11 to 16 to 21. What do you think the next one probably is? 26, and then what? 31. So you can also be on the lookout to see if you happen to see a pattern for what's going on so that you don't have to physically keep plugging the numbers in. So these are my first 5 terms of this sequence. So this is sort of letter I. The second thing we're supposed to do is to decide, is it arithmetic, geometric, or neither? So what do you think? Okay, so Amy says arithmetic. Do you guys agree? Yeah. So why is it arithmetic?
You're adding 5.
You're adding 5 every time. take a look back at the equation, the formula. Why are we adding 5 every time? What about that formula says that's what's going to happen? There's no exponent, that's one thing. What else, though? Right, it's the number in front of n that's in that arithmetic form. It has the right form for an arithmetic sequence, too. So, yeah, this one's arithmetic. Fabulous. Okay, next one. We're plugging in, same thing, the numbers one at a time. So I have 1 squared minus 1, which gives me 0. And then I have 2 squared minus 1. That one's 3, right? 3 squared minus 1. 8. About 4 squared minus 1. 15. And 5 squared minus 1. 24. So our sequence of numbers is 0, 3, 8, 15, 24. Notice I didn't actually pause and say, do you notice a pattern? Because that one wasn't quite so obvious that there was really anything going on that was like the last one, so I didn't mention it. Is this arithmetic, geometric, or neither? This one's neither, actually, right? That 0 at the beginning already makes things not be able to be geometric. I can't take the 0 at the beginning times anything and get to 3. It's not possible. It's not geometric. And going from 0 to 3 is adding 3, but 3 to 8 is adding 5. Now I want to show you there is a pattern. This one's neither. I'd like to show you the pattern because you're going to see something come into play in your homework that has the same feature. Before I do that, let's answer part C. Is this inductive or deductive reasoning? What do you think? This one's deductive. Deductive means that we start out with a concrete rule, and then we make our predictions based upon a rule instead of upon a generalized pattern that we've created. So this is a rule that we're given. It's got an equation or a formula, kind of a perspective. It's not an equation, an expression or a formula, and you're actually using that to evaluate something. So this is deductive reasoning. All right, so I'd like for us to take a look at the 0, 3, 8, 15, 24. No, I'm going to need to do it over here. You know what? Let me give myself an extra slide. Okay, so 0, 3, 8, 15, 24. I'd like to pretend like I'm trying to find out if it's arithmetic and find the values that add on each value, okay? So if I were to take and I were to go from 0 to 3, what would I have to add to do that? 3. How about from 3 to 8? 5. How about from 8 to 15? What about from 15 to 24? Now I'd like for you to look at the numbers 3, 5, 7, 9. Do you see a pattern there?
Yes.
3, 5, 7, 9 is actually an arithmetic sequence, isn't it? If I did the same thing again, in other words, I did this, I'd notice that these are all 2 apart. You may have thought, hey, these are all odd, and that's true as well, but they're all 2 apart. This process actually has a name. This was actually called the first differences. So if that's the first differences, what do you think this next line is? The second differences. And if you still didn't have the same number there, you could go on to the third differences or the fourth differences. So even when a pattern is given to you and it doesn't fit this arithmetic or geometric form, you do have the ability to look and see if it has a second difference form you can match up or pattern that you can sort of figure out, or a third difference or a fourth difference. And there are some examples in your homework and your group work that you're going to be doing that too. Okay? All right, let's go back then, or go on to example 3. Example 3 says that it wants us to find a counterexample for the following. Do you remember we encountered that word counterexample before, I believe, last time? What does counterexample mean? Yeah, it shows something's false, okay? So a counterexample for this means it's going to be some example, some number, in this case n, that shows that when you plug in that number for n plus 5 over 5 is not the same thing as n plus 1. So a counterexample simply means finding a value that makes it not work. So somebody give me an example for n that would make this not work. 5. You know what, Amy? It's like you're reading my notes because that's my example written down too, actually. And so we're going to actually show it makes it not work by plugging it in. So 5 plus 5 over 5. So what is 5 plus 5 over 5? What actually is it for real? It's 10 over 5, which is what? 2. Now that's the left, this is the left-hand side of my equation here, right? And then I'm going to do the right-hand side. So the right-hand side says I should be taking n, which is 5, plus 1. What is 5 plus 1? 6. And the last time I checked, and the last time you did too, these are not equal. Right? Now, the reality is it would take a very, very, very specific example to actually make this true. What number for n makes this true? Do you know? It's 0. If n equals to 0, this will actually work. Any other number won't. It's the only one that actually will. And that's usually the case with a counterexample, not always. But it's often the case with a counterexample is that there's something that shows that it either is very common, it's an easy one to find because everything practically works, or it's a number that's easily picked, like the number plugging in the number 0 here actually made it work. It was very specific, but sometimes the number 0 is exactly what you need to make something not work. And that happens sometimes too. So what reason do you think, if you saw a student do this, the student might have thought this made sense? What would they have possibly done to think that that would work? Any thoughts?
They would think that 5 over 5 is equal to 1, so both ends are being added to 1.
Yeah, and they usually do it in a very simple way. They usually do something like this. And they say, oh, look, I divided it. And they don't realize, yeah, but I never divided the n. Right? They divided, definitely divided, but they forgot that they didn't divide all of it. They only divided part of it by 5. So the idea means that they probably reduced but they either forgot or didn't know that they had to reduce both pieces. So in reducing, in this case, is dividing. Whoops. Both n and 5 by 5. They just divided the 5 by 5. And part of that is our fault as teachers sometimes, is that we're not real careful about our language on how we reduce things. We talk about things canceling out a lot. You know, they match up and somehow they cancel. So we want to be really careful when we talk about that and when we show this kind of a process to a student. So what would be better to do, instead of drawing what we did, is to recognize, say something like that n plus 5 over 5 is really n over 5 plus 5 over 5, and then recognizing that this value is equal to 1. You guys see that okay? So sometimes more steps helps to clarify things, and that's helpful. All right, figurate numbers. These are fun. These you'll see happen a lot at younger grades because they're very visual things. So figurate numbers are based on visual or geometric patterns. These are examples that are neither arithmetic or geometric, and such numbers that are represented by dots arranged in a shape of certain geometric figures. So here's an example of one, triangular numbers. So some triangular numbers look something like this. So we'll see how good I am at making my dots today. So you have 1 dot, and then you have 3 dots, and you have the dots like this. And then like this, and I'll pause for a moment. So there's a pattern. You can definitely see the pattern changing each time. What would the next figure in our sequence look like? What's the shape of these figures first? Overall, we have a triangle, right? How will the next shape change from the shape before? Yeah, there'll be 5 on the bottom, right? It's almost like I'm just introducing an extra layer beneath it, right? And beneath this sort of a triangular shape or this pyramid kind of shape. It's underneath it. So the last one had 4, so this one will have 5. And then we off-center a layer above with 4, 3, 2, and 1. There is a numerical association with this. We can actually count the dots. Okay? So if I do that, the first one had 1 dot. What was the next one? 3, and then 6, and then 10. And my last one, the one that we just created together, was what? Was it 15? Okay. So I want to show you this again because it's interesting. If we were to look at this sequence of numbers, they are not arithmetic or geometric, right? So let's try to do that differences thing that we did on that other slide. So this is 2. 3 to 6 is actually 3. 6 to 10 is 4. 10 to 15 is 5. And do you see a pattern? Yeah. It's the second differences that are actually all the same, right? Yes, it is. So it's what's called a common second difference. It doesn't have a common difference. Those were 2, 3, 5. You know, those are not the same, but they have a common second difference. We also have square numbers, and so square numbers look something like this. We start out again with 1 dot. I should make that a little bit lower. Let me try that again. 1 dot, and then our dots look like this. And then something like that. And like that. So you tell me, what would the next figure look like? Five on the bottom. And how tall? 5 tall. Sorry, my shape almost looks rectangular. It really isn't supposed to be. It's just my spacing's a little bit off, okay? Let's write the pattern out though now. So the first one is a 1. What's the next one? 4. 9. 16. 25. I'm going to guess you could probably write an equation for what's happening, right? It's just n squared, right? Whatever n is, it's the squared of that term. And that's fine, but I'd like for you to see again that we could still do that differences pattern approach. And we can still say this goes from up by 3, this one's up by 5, up by 7, and up by 9. And sure enough, look at this. The second differences are all 2. It's got a common second difference. Okay, here's the last one. I think this is a fun one. There's a typo in your slides, I believe. I don't think I got this one fixed accidentally. In fall of 2011, so this was my second year at OBU, we had just created the 6 different colleges that are a part of our university. And one of our colleges, the college that I'm part of, is the College of Science and Math. I always want to say math and science. I definitely think it should be math and science, just saying, okay? You guys are a part of what college? Do you know what yours is called? Arts and Humanities, yeah. So there are 6 colleges, but the newly formed college is called the Hurley College of Science and Math, and we had a meeting. And on the board, the value 3.1415 ... was written exactly like that, was written. And our dean asked us to write the next 2 terms, not 5, the next 2 terms in a sequence of numbers. So I want you, without help from anybody else, to just decide what you think you would do if I asked you to do the same thing. What is the next 2 terms in this sequence of numbers? What comes after the 5? Okay? So write down your guess. What would you say are the next 2 terms? Again, I don't know why I've got 5 on this slide. This is weird.
So just guess by the pattern, not because you know what the rest of the pattern.
You don't know the rest of the pattern. You're just being asked to guess what the next 2 terms are. Okay, and after you to guess what they are, I want you to explain your reasoning. Okay, there's not a right or a wrong answer to this question, okay? Write down what you believe the next 2 terms are and why you think that's true. All right, somebody suggest what you have for your next 2 terms. 1/6? Okay, so just show of hands, who has 1/6? Okay, does anybody have anything else? No? Gretchen, what'd you decide? Did you do 1/6 as well? Or did you do something different?
I kind of found 2 different things.
What is your other thing you found?
This is commonly known as pi.
Okay.
1.159, so the next one was 9, but I don't remember the rest of it.
The next one's 2.
If you
Mm-hmm.
do it the way that it looks like you're going to make it 6.
Okay.
If you knew what pi was, you would know that it was not easy.
Okay, so one issue is exactly what you're saying, is that just looking at the number, we don't know what the pattern is, so we're sort of left to our own devices of what our prior knowledge and experiences are, right? So you guys are definitely in the mindset to write down 1/6 because that's what we've been looking at, is that kind of a pattern in this section, right? 1/6 is the very natural what I should write down. Everyone in our room of scientists and mathematicians, what do you think we wrote down? 9/2. We wrote down 9/2, okay? Because we did the same thing that Gretchen started describing. We looked at it and we said, well, it's just pi. That's pi. I mean, that's the decimal approximation there. She's asking us for pi. And what was interesting is most of you wrote down 1/6 and you didn't even think, like, is there another option? In our meeting, all of us wrote down 9/2, and none of us even had any kind of inkling that there would be another option. We just thought, well, of course it's 9/2. Just like you guys thought, well, of course it's 1/6. Okay? So there are 2 different legitimate answers because what kind of reasoning is this? It's inductive. Inductive reasoning means that we take a pattern and we try to figure out what the pattern is and generalize it to what comes next. So what does this problem indicate to you about inductive reasoning? It's not always right. Right? There's some kind of sense that sometimes you might end up with things that were unexpected or not exactly what was going to or intended for you to find. Okay? Sometimes there's more than one legitimate generalization to a problem. We're going to stop there.